today as we're losing that. Another thing is features. We can make our systems easier to use. Things like file searching is a great opportunity. A third thing people look at is security. How do we sort of make sure that only authorized users can do authorized things? And finally, there's a problem of reliability. How do we make sure that the machines are available when we want to use them? So when I started this project, I was actually an architecture student. I was working on simultaneous multithreading, and I was looking to see what kind of great things could we do with threads. And first, I was looking at performance. And that was too hard. All the architecture performance things were like a 10% improvement, and that didn't really thrill me that much. So I went around the hallways of the University of Washington, and I asked people, what kind of cool problems do you have that I could work on? And pretty much everybody said is, I'm doing okay, but the real problem is my computer keeps crashing. And if you could fix that, I'd be really happy. And so I decided, well, maybe that's an interesting problem. And it brought to mind a lesson that my advisor had told me, that if you're trying to get your work done and you keep on getting hit in the head with a frying pan, maybe you should fix the frying pan instead of doing your regular work. So this is what I decided to work on, operating system reliability. And the first thing I did was to see what have people done before. And if you look at previous approaches of what people do for reliability, there's really sort of three major things. One thing people do is they say, well, we've got a big system. It has bugs in it that's making it crash. Let's fix the code. So Dawson Engler at Stanford has a meta-compilation tool that turned into Coverity that finds bugs for you automatically. Microsoft has their Windows static driver verifier that finds bugs in drivers automatically. And this is a pretty good approach. Now the problem is that Windows has like 30 million lines of code. So if you have, one bug every 1,000 lines or something because you're an amazing programmer, you still have 30,000 bugs you have to fix. And there's also no guarantee that these tools find all the bugs or even the most important bugs. They find sort of the bugs that are easy to find in general. One other thing you can do is you can say, you know what, the systems we have today are fundamentally unreliable and broken. They're never going to work. We need to throw them out and start from scratch. So this has been done with things like the Singularity system from Microsoft, the nonstop operating system from Tandem, or IBM's Quicksilver. And this is good. You can build reliable systems this way. This is how the space shuttle was done. They didn't start with Windows. It's a whole new system. The downside, though, is that you're throwing away $10 billion worth of investment or hundreds of billions of dollars investment in your existing system. And so it's a pretty expensive thing to do, and it takes a long time. And by the time you get it done, the system you were trying to copy or build on, you're sort of trying to make work better, is changed, and it does new things, and you're always playing catch-up. So it doesn't work so well for sort of the commodity market. Well, a third thing you can do, and as an architect at the time, this was very interesting, was can we add hardware to solve this problem? So certainly in the server space, people looked at clustering as a solution for high availability and reliability. Things like VAX clusters, Microsoft's Wolfpack product, or the Google cluster is a great example of this. Now this has been very successful. If you have two computers and one crashes, you still have one running, you can still get your work done. The downside, though, is that it doesn't work very well for most people. So when I travel and I give talks, I don't bring two laptops to handle the case where my laptop crashes. It's really not feasible at the low end to make this work. So what's needed is a fourth approach. And what I proposed to do in my work was to say, okay, let's try to focus on the big problems. What is it that makes systems crash the most? And what can we do to the systems to prevent that? Let's try to see if we can build fault tolerance into the system as a new subsystem instead of re-architecting everything. So to do that, we need to understand what operating systems look like and why they fail. So this is a picture of an operating system. Probably everybody saw it in the undergraduate class. Up at the top in blue are applications. They're isolated from one another. This means that there's a bug in one application. The other ones keep running. The kernel keeps running. Down below that red line is the kernel. And this has subsystems like virtual memory and filing and networking. And this has no isolation, meaning if there's a bug here, it can corrupt the whole system and crash. Now it turns out that the kernel we're looking at right here is actually pretty reliable. The code in here is pretty stable. It's written by people with a lot of experience. It doesn't crash very often. What's missing from this picture is actually the most important thing that runs in the kernel today, or the biggest thing that runs in the kernel, and of course, that is device drivers. Device drivers account for a huge amount of the code that runs in the kernel. In my Mac laptop, it's something like 75% of the kernel code is in drivers. And drivers turn out to be the #1 cause of crashes of today's commodity operating systems. I learned from people at Microsoft that 85% of the crashes of Windows XP are due to faulty device drivers. What this means is that no matter what you do to the rest of your system, if you don't fix this problem, you'll never have a reliable system, because you can only get like a 15% improvement in reliability unless you look at device drivers. So this is the problem that I want to solve. And the way I want to do it is to add a new reliability subsystem into the kernel, just like we have other subsystems. The job of this reliability subsystem is to isolate device drivers, very similar to the way that applications are isolated. What this means, if there's a bug in a device driver, the rest of the system keeps running. Now, another goal that I have for this to make it work in commodity systems is compatibility. I don't want to have to rewrite everything to make it work. However, there may need to be small changes made to other pieces of the kernel, shown here by the pink triangles, to integrate this new code. So in summary, or what I'm going to, not in summary, but in introduction perhaps, the contribution of the work that we did at Washington was that we built a new kernel subsystem that prevents the majority of driver-caused crashes. It requires no changes to existing drivers, requires only minor changes to the operating system, and only minimally impacts performance. So in the rest of this talk, I'm going to talk more, first of all, about what a driver is, why they cause problems. I'll sort of give you an overview of my solution. I'll then talk about the design of this new subsystem that I built, and then I'll evaluate. First, I'll look at how complex is it. Is it something you could feasibly add to a system? I'll look at, does it actually do what I said it does? Does it actually make your system more reliable? And I'll look at the performance cost. How much do you lose by using something like this? And then I'll summarize. So let's start off with sort of driver 101. What is a device driver? Well, sort of abstractly, a device driver is a module that translates requests from the operating system into a request for a specific device. For example, a network device driver takes requests from the kernel to send and receive packets, translate those into some language that the network device itself understands, and then tells the card to go do that. In general, every device has its own unique driver, and that means there's tens of thousands of different drivers out there. For example, for Windows XP in 2003, there were about 35,000 different drivers. And if you count all the versions of those drivers, there were closer to 100,000 different drivers that you could run on Windows XP. In addition, every single machine has a lot of different drivers in it. My laptop, as I said before, it's a Mac. It has 81 different drivers running in it. And they control everything from the display to all the connection devices, the keyboard, the internal buses. All these things have drivers that run in there. And they all run inside the kernel, meaning there's no isolation for any of this. Now, one problem is, how do you get 81 different pieces of code that the kernel writers didn't know about to run inside a kernel? And the way this works is the kernel understands a small number of common interfaces. For example, it has an interface for network cards, and it knows how to send a packet. It's up to the driver writer to implement this interface to actually do the real work of sending and receiving a packet. Let's look now at why drivers fail. Well, at a high level, drivers fail because they're complex and hard to write. Now, when I gave a practice talk, somebody pointed out this was a silly answer, because this is why all software fails. All software is complex and hard to write. And so the question is really, why are drivers different than everything else? And I decided there really were things about drivers that were different that made them genuinely much more difficult to program than, hello world. So one thing is that drivers are sort of fundamentally asynchronous. They deal with an outside device that can generate interrupts at any time. They deal with a kernel, which may have lots of threads in it, so they can be called on different threads simultaneously. So they have to deal with lots of different asynchronous events. Second, they run in the kernel, and the kernel has a very rigid set of programming rules about what you can and can't do. For example, there's rules on when you can allocate memory, how much memory you can allocate, whether that memory allocation can block or it can fail. There's rules on what pages in memory you're allowed to touch. There's rules on what priority level you have to be to call certain things. And in general, these rules, while you have to follow them, if you don't follow them, most of the time your system works fine. It's only when the moon is blue and something else goes wrong that these rules actually count, which means that through normal testing, it's very hard to find if you actually broke one of these rules. What this leads to are lots of non-reproducible failures, where your machine crashes, you boot it up again, everything keeps working. It's very frustrating for the user that it crashed, but the benefit is that at least when you reboot, things start working again. But for the driver writer who wants to fix these, it makes it very difficult, because it's hard to reproduce and track down these failures. Finally, drivers are very difficult to test and debug. They run in the kernel. If you've done any kernel programming, you know that this is inherently a difficult environment. And they deal with this device. And it's hard to make the device generate all possible inputs to sort of get good code coverage of the driver. Now, finally, drivers, relative to other kernel code, are written by less experienced programmers. If you think about sort of the core team in Linux that works in the kernel, or the core team at Microsoft or Sun that works on their operating systems, those people have a huge amount of experience in this environment. They have a very good support network of people who understand these rules and can help them out. Whereas driver writers are more often isolated on their own in a company that didn't produce the operating system, and they're less familiar with these rules. And also, their drivers are not as widely tested. Microsoft beta tests their things on millions of machines, and driver writers don't always have that benefit. So let's look now at what happened when a driver fails. Again, we have our picture of an application in the kernel. The application here is calling into the driver. What happens if this driver fails, for example, by writing through a bad pointer? Well, one thing it can do is it can overwrite its own state and corrupt internal driver state, making the driver malfunction. Another thing it can do is it can overwrite application state because it's privileged. It can overwrite anything in physical memory. It could corrupt the application. Now, the worst thing it could do is that could overwrite kernel state. And the kernel is really not built to tolerate this, and this is what makes your whole machine crash. This, in a nutshell, is what I'm trying to prevent, a buggy driver from corrupting either your application or your system. As I said before, the way I'm going to do this is by isolating drivers. Here, again, the big blue box. What this means is that if there's a bug in a driver, we're not going to let that bug escape and corrupt applications or the kernel. However, what we do need to do is the way to keep your system running. If we just detected a failure or isolated a driver and did nothing else, it wouldn't be a very useful system. Because it turns out that drivers are actually something you really want to have working. If I had a machine here with no drivers, I would have a brick. Because drivers are the only way you can interact with a machine. So it's very important after a failure to recover in some way. And the way we can do this is by, for example, restarting the driver. Now, there's two things that we have to worry about when we restart the driver. One is, what happens to applications? An application may have downloaded some state into the driver. And if we just restart the driver, that state may be lost. So we need to worry about that state. The second thing we need to worry about is what happens to applications who are trying to use the driver while we're restarting it. What if they, can't find the driver, they die or something like that? This is actually pretty common that applications don't check error return codes because they assume that drivers are 100% reliable. What do we do about that? So these are the two problems we need to solve during recovery. So the objective of my work is to eliminate most of the downtime caused by drivers. I'm not looking for a 100% solution here. First of all, drivers are not 100% of the problem, so even if I had a 100% solution, it wouldn't make your system perfectly reliable. And second, 100% solutions are typically very expensive and impractical. And so really, I'm looking for a best effort solution. If I can prevent 80% of the failures caused by drivers, I think that would be a worthwhile thing. So really, I'm trying to prevent system crashes with isolation, and I'm trying to keep applications running with recovery. This is really the top-level goals of my work. So I'm now going to talk about the design. How did I actually build this? I started off with a standard Linux kernel, standard Linux drivers. I added in a new subsystem that provides these services in a way that's compatible with existing code. Now, what I mean by compatible is a couple of different things. First of all, it means no changes to drivers. There's lots of drivers out there. I don't want to have to make any changes to them because there's just too many if I get into that game. Second, no changes to applications. You could imagine some kind of architecture where you can return errors, and applications now have to check return codes from every system call that accesses a driver and do something different if it fails. I think that's a non-starter. So I want applications to work better without doing anything different. And third, I want almost no changes to the kernel. No rewriting things in new programming languages, no restructuring, just some sort of minor integration hooks here and there to add in this new subsystem. So the way that I accomplish this is by architecting the subsystem as a layer. I call it the Nooks reliability layer, and it sits between device drivers and the kernel. The layer internally is composed of 5 different components. First of all, there's an isolation mechanism called lightweight kernel protection domains that prevent application drivers from overwriting kernel state. There's a communication mechanism called extension procedure call, or XPC, that is used for invoking drivers safely. There's a table of all the objects currently in use by a driver called the object table. And this is used for recovery and a couple other things, so we can sort of clean up what the driver's doing. There's a recovery mechanism called shadow drivers that sort of manages transparently recovering the driver without letting the application know or the kernel know anything happened. And then finally, there are wrappers that allow all this code to be seamlessly integrated into a system without changing either the kernel or the driver. So let's look first of all at isolation. How do we prevent drivers from crashing your system? So again, we have a picture of an operating system kernel here. And really the problem that I'm trying to solve is that a buggy device driver can overwrite kernel data structures. That is sort of the key problem that I want to stop from happening. One thing a lot of people proposed is, well, let's get drivers out of the kernel. Let's move them up into user mode instead, like in a microkernel. And this has some attractions. The downside, though, is that drivers are not written to run in user mode. They directly access kernel data structures. They call kernel functions directly. If you move them into user mode, you sort of need to re-implement all of that information. And so it's a huge amount of work, or it's not very compatible. However, we can leave them in kernel mode if there's some way we can prevent them from overwriting the kernel data structures. And I do this with what I call lightweight kernel protection domain. This is an execution environment in kernel mode, meaning it's fully privileged, in the kernel address space, meaning that kernel pointers have the same meaning in a kernel or in a protection domain. The difference is that the protection bits for kernel data structures are different. Whereas the kernel is allowed to read and write everything in the kernel, the driver can read everything in the kernel, meaning you can pass data to it with no work whatsoever, but it can only write to its own private data structures. It's had its own private stack and its own private heap for doing memory management. But anything it wants to write to has to be allocated from that stack or that heap. And in this way, we can use the page protection mechanism of the processor to isolate device drivers. And we do this basically by creating a shadow copy of the kernel page table with the same mappings that we keep synchronized, and we just change the protection bits. So another question is, how do we invoke a driver? How do we make sure that we actually run with the right protection information? So normally the kernel and the driver interact through procedure call. And what we need to do is make sure that on every procedure call, we change protection domains. And I do this with a new mechanism that I call an extension procedure call. And I replace every procedure call with one of these new XPCs. An XPC is conceptually like a remote procedure call in distributed systems or a protected procedure call in capability systems, and it combines a control transfer with a protection domain change. So by replacing every function call with an XPC, we can make sure the driver runs in the correct protection domain, and when it calls back into the kernel, we return from this, and the kernel runs with its correct privileges. Under the covers, basically an XPC, all it is it's code that changes the stack pointer, changes the page table, and then copies the arguments onto the new stack. That's all it is. It's pretty simple. So this handles control transfer. The next question is, what about data transfer? You know, drivers deal with data. They exist for getting data on and off devices into the kernel. How do we handle that? Now, the problem is that existing drivers expect, on some occasions, that when they're passed a piece of data, they're allowed to write to it. Like, they need to be able to fill in buffers with data, or they need to be able to sort of fill in control fields on other objects and things like that. And if we just pass kernel objects directly into the driver, they'll page fault when they try to write to this because they don't have permissions. The way that I solve this is by creating a shadow copy of any kernel object that the driver uses. The shadow copy is allocated off of the driver's heap so that the driver can read and write to it. And then I synchronize the driver's version with the kernel's version of this object every time control passes back and forth between the driver and the kernel. To keep track of this association, I use a data structure called the object table that keeps basically a reference of all the different objects, kernel objects the driver is currently using, and the association between the kernel version and the driver version. This serves a couple of purposes. One, it allows me to map between the two different versions when calling between the kernel and the driver. Two, it's a great way to check errors. If the driver passes something into the kernel that's not in the table, by definition it's an error. It's passing some kind of bad pointer. It might be a totally wild pointer. It might be something it freed already and was removed from the table. And third, this is a great thing to use for cleaning up after a failure because it lists all the kernel objects the driver is using. And so to recover after a driver fails or unload it, all we need to do is walk through this table and release all the resources, and then everything the driver did is gone from the kernel. So the final thing is, how do we make sure all this code gets invoked? We don't want to rewrite the kernel or the driver to actually invoke the XPC code or this data copying code. So I used what I mentioned before, wrappers. Basically, wrappers are code that implement the same calling interface as the driver and the same calling interface as the kernel. When I load a driver into the kernel and I want to protect it, I link it against these wrappers instead of the kernel itself. And the wrappers then handle all the XPC and the data copying code. In this way, this injecting this protection is totally transparent both to the kernel and to the driver. Now, the nice thing is this adds a lot of flexibility because the existing kernel functions are still there. So when I load a driver, I can choose, do I want to protect it? Do I not want to protect it? You might start off not protecting anything. When you get some failures, you might decide you want to protect some things, depending on your system. But this means that we can sort of totally transparently, without modifying the driver and almost no changes to the kernel, add this protection and recovery mechanism. So that was all about isolation, meaning how do we stop drivers from crashing your system? The next piece is recovery. How do we keep your system running and get that driver up and running again after a failure? So there's two things that I want to do in recovery. The first thing I want to do is get a driver back into a state so it can process requests as if it had never failed. So this means that if an application was talking to a driver and configured it in some way, and the driver fails, we want to get the driver back to a state where the application can just send another request without doing anything else, and that request should be handled correctly. The second thing I want to do is conceal the failure. Now, concealing failures is often seen as a bad thing, particularly in distributed systems where you can't really conceal things, just because you can make things worse by concealing failures. But in some cases, I think it makes life better, and this is one of those. Basically, the goal here is to make sure that applications don't actually see that the driver failed. They shouldn't see any incorrect return codes. They shouldn't see any errors. They shouldn't see any weird behavior that a driver shouldn't do, so that the application and the operating system should keep functioning correctly. Now, we thought a lot about how to solve this, and we had ideas like putting wrappers around system calls that would handle this code. But we had the realization that the interface to the drivers actually says a lot about what the driver has to do to respond to a request. For example, when you send a packet to a network card, that network card has two choices. It can send the packet or it can not send the packet. It can't go and reformat your hard disk. What this means is that the kernel has to know what a driver does in response to calls, and we can leverage that to handle recovery. We can basically model the driver as a state machine that changes state every time it interacts with the kernel. So let me show you how this works. So we start off with our initial state. Say it's a network driver. When we send a packet, the driver is now in this abstract state where there's a packet that's in flight. It may have been sent, it may not have been sent. We don't really know, but we know that it has a packet in its hand somewhere. When the driver tells the kernel that it's completed this packet, we know that it's back in the same state it was in the beginning, that sending a packet has no long-term effect on the driver's state. And so suppose the driver crashes at this point, we know we don't need to do anything because it's in the right state already. So there's more complex state machines for other drivers. Here is an example of a sound card driver that you can open and close and then reconfigure in a couple of ways. Now, what this means is that recovery basically boils down to advancing the driver from the initial state into the state it was in at the time of failure. And if we want to, we can follow the exact path that the application did to get it there, or we can find a shortcut path to get there more directly. For example, dropping loops from the graph or something like that. That's sort of how do we get the driver into right state. The second thing is how do we conceal failure? And what we'll do here is we will reply to requests with responses that are valid according to the state the driver is in. So we'll rely on the state machine to know, what is the next thing a driver could do, and we'll pick one of those as the right way to respond. The way that I do this is with a new kernel agent that I call a shadow driver. And a shadow driver is a piece of generic code, meaning that it's not specific to any particular driver. Under normal operation, it records state-changing inputs to kind of figure out where the driver is in the state machine. On a failure, the shadow does three things. First, it restarts the driver. It then replays this state, the inputs, to recover it back to the right point. And while this is going on, it emulates the driver to applications in the operating system so they're unaware of this failure. In general, it takes between 1/10 of a second and a couple of seconds for the driver to recover. Now, it's important to notice that the shadow driver is not a real driver. It can't actually make the hardware do anything. And the way I like to think about this is that the shadow driver is sort of like the small spare tire that comes with modern cars. This tire is good enough to get you across town to the garage. It's not good enough to drive cross country. And that's what a shadow driver is. It's good enough to keep your application limping along until the driver comes back, but you can't actually run with it for very long because you can't actually interact with the hardware. So I said before that shadow drivers are generic code. And that's true, but they're not 100% generic. I do specialize shadow drivers to a class of drivers that have similar properties. For example, I have one shadow driver for all network drivers. What this means is that that shadow driver can then take advantage of the characteristics of a network driver to handle the logging and the emulation more efficiently. So let's look now at how this actually works. So again, we have a picture of the kernel. I changed it a little bit here because I really want to focus on the communication between the kernel and the device driver. So to this picture, I add a shadow driver. The job of the shadow driver under normal operation is to follow around the device driver, watch what it's doing, and be prepared to step in at a moment's notice. To make this work, I add a new mechanism that I call a tap. A tap is conceptually a T-junction that sits between the kernel and the device driver, and every time the kernel makes a request, the tap then sends this request both to the device driver and the shadow driver. The same thing happens in the reverse direction. What this means is the shadow driver sees every piece of communication between the driver and the kernel, and it can log whatever it needs to. So, to prepare for recovery, the shadow driver needs to record any state-changing input. And there are really three kinds of state-changing inputs. One kind is an I/O request that's in progress. As I said, if you send a packet, you're in a state where there's a packet outstanding until you complete that send. And so the shadow driver has to know what I/O requests are in progress that we might need to resume or cancel after a failure. A second thing that we need to recover are configuration settings. If you configure a network card to be to do TCP, to do offload checksumming or something, or you configure your network to be 100 megabits instead of 10 megabits, we need to remember that information to recover from a failure. So the shadow driver has a log where it stores this configuration information. The third thing the shadow driver needs is information about connections. Some drivers have connections that an application can open and then configure. For example, sound cards are connection-oriented, so every time you open a sound card, there's a new connection, and this connection remembers things like the bit rate and the sample size and the sample format for this connection. And the shadow driver needs to remember that information so it can recreate the connection after a failure. So let's look at what happens when a driver does fail. Here, first of all, we need to detect a failure. And this can happen either through hardware or software. If the driver tries to write to a bad place in memory, the processor will detect this, trigger an exception that will then cause the system to call into the shadow driver and start recovery. If the device driver passes a bad parameter into the kernel, then the wrappers will detect this and will notify the shadow driver that something failed. Now, some failures you're never going to detect this way. For example, suppose your network driver sends half of the bytes in every packet. There's no generic way to detect that because you have to know you have to sort of be the recipient to know what happened. So you can also have a user mode agent, or a kernel agent for that matter, that can notice that something failed and can trigger recovery. I sort of envision this as another red X at the top of your applications that you can click on when something goes wrong, you don't know what happened. So the first thing that happens when a device driver fails is the shadow driver immediately isolates it from the rest of the system, so it can't corrupt the kernel. It does this by changing the mode of the tap, so the tap no longer lets any communication go into the driver. It then sort of unloads and reloads the driver, so it's back in the state it was in when it was first loaded off disk, and it then proceeds to initialize the driver. It does the same exact thing the kernel does when initializing a driver. And the nice thing about this is that we're sort of leveraging existing code in the driver to recover itself. We don't need to add new recovery functions to make this happen. We're just initializing it the same way the kernel does. Now, while this happens, the driver may try to call into the kernel, for example, to register itself as a new driver. The kernel thinks the driver is still running, so the tap instead sends this to the shadow driver, and the shadow driver pretends that it's the kernel so that the driver thinks that it's loading and initializing normally. Once the driver is up and running, the next thing the shadow does is has to replay its log of configuration data to reset the driver into the right state, reopen any connections, things like that. And when it's done, it'll sort of open up the tap again. So in summary, shadow drivers recover from a failed driver by resetting the driver, reinitializing it so it's in the state when it was just loaded and initialized by the kernel, and then replaying any log requests. Yes?
Wouldn't that cause the driver to fail again if it had a bug?
Everybody asks, that's a good question. What happens if the bug happens when you replay the log request and it fails again? Well, if that happens, you have two choices. You can decide not to replay the log requests and say, screw you to the applications. You can fail, but our system won't crash, and we're not going to replay those. Or the other thing you can do is you can actually record those operations that made the driver fail into a file and then ship them off to the driver writer and say, here's the sequence of calls you make into this driver that makes it fail 100% of the time. Please send me a fix. Yes?
So does the shadow driver communicate with the tap, or is it in control of the tap when the driver crashes?
The shadow driver controls the taps, and it can sort of turn the knob on the taps as either being open or closed effectively. Okay. So this was how we recover a driver. The next question is, what happens to applications while all this is going on? So, as I said before, the shadow driver is responding in place of the device driver. So when the kernel calls into the driver, the tap sends this call just to the shadow. And the shadow then responds as if it's the device driver in a way that keeps the kernel and applications running. So the goal is to respond with valid possible requests so that hopefully the kernel and application will already have code that deals with this response. And they actually will not be aware that anything actually failed. Now, the thing to remember is the shadow cannot actually control the hardware. So it can't respond in a way that actually requires controlling the hardware. Like you can't actually fabricate network data to return to somebody if somebody wants to read from a socket because there's no data to return. So instead, you need to sort of hold them off in some way until the driver's up and running again. In developing this, we came up with 5 general strategies for responding to requests from applications while a driver has failed. Now, the best thing you can do is do exactly what the real driver would do. Suppose, for example, that you're querying a property of the driver, some configuration setting. Well, that information is already in the log, so the shadow can just return that information directly. It's exactly what the real driver would do. Everything is perfect in this case. Well, another thing you can do is you can say, I can't do anything now, I'm too busy. And this is sort of a unique feature of device drivers. The nice thing is the real world is rate limited. You can't send unlimited amounts of data out into the real world through any normal device. And so every device driver has the capability of telling its clients, I'm too busy now, I can't take any more data. And we can leverage this during recovery by just pretending that the device is busy right now. So if you try to send a packet while you're recovering a device driver, the shadow driver will say, you know what, my queues are full, I can't take this packet right now, call me back later. And the kernel says, fine, I understand, just let me know when you're ready, I'll come back later. And it works perfectly. You don't have to do anything else, and the kernel will stop contacting the driver during the whole recovery process. Now, this doesn't work for every single way that you can call a driver because some calls are not dealing with the device, and so they're not rate limited in this way, and you can't stall them. So one thing you can do is you can just block the caller directly. Put them on a wait queue and wake them up after recovery. Now, again, this works in some cases, but you can't block all callers. For example, blocking a timer callback or an interrupt callback is a bad idea because it deadlocks your system. So what you can do in that case is you can either queue the request, put it on a queue and handle it after recovery, or you can just drop the request if it's something you know is safe to drop. For example, suppose it's an interrupt handler, you can just drop the interrupt handler. You don't have to worry about that. Using these 5 general strategies, shadow drivers can conceal the recovery of a driver from applications long enough for the driver to recover. So, in summary, Nooks provides isolation using lightweight kernel protection domains. It invokes drivers with extension procedure call. There's an object table that tracks all the kernel resources in use by a driver. And there are wrappers that make all this code transparent. And it recovers using shadow drivers. So I now want to move on and talk about the evaluation. First of all, I'll talk about the implementation complexity. And then I'll talk the benefit, and then about the cost. And one interesting anecdote is when I was preparing this talk, we were trying to debate, do we talk about performance first, or do we talk about the benefits first? And my advisor said, suppose you're a car company, and somebody said, I have this great thing, they're called seat belts. They'll make everybody really safe. And the car company came back and said, that's great, how fast will my car go? And so for that reason, I don't think I want to talk about performance first, because really this is about making your system safer. It's not about making it faster. And performance is not the right question you should ask when looking at a reliability system like this. So first of all, the implementation. I implemented this for 3 different classes of drivers, 14 drivers total, and I'm only going to talk about the ones that are shown here in red. The other ones were substantially similar, and what we found in general was that once we implemented the system for one driver in the class, the rest of them followed fairly naturally with almost no changes. Sometimes we'd have to write an additional wrapper because there was a new call that it made, but in general, things worked out quite smoothly. Now, in terms of the implementation complexity, I want to break it down into 2 kinds of code. First of all, there's changes to existing code. This is, of the existing code in the Linux kernel, how much did I have to change this code? And I counted it all up, and it was about 924 lines of code out of a total 1.1 million lines of code in the kernel, about a little less than 1/10%. And this is those little pink triangles. This is the integration complexity of adding this to your system. And there's really 3 kinds of code. It's the exception handlers to detect when there's an exception in a device driver. It's memory management code to synchronize page tables. And then there's some code for loading modules into a protection domain that has some complexity also. Out of the 50,000 lines of device driver code, I didn't change any of that. So I hit my goal of being 100% compatible with device drivers. I did have to recompile things, though. And that's sort of an artifact of the Linux kernel where you have to recompile your drivers pretty much every other day anyway. So the second kind of code is new code. And here I break it down into isolation code and recovery code. The isolation code was about 23,000 lines of code. And the reason it's so big, I don't know if this is big or small or not, but the reason that it's this size is that there's about 700 functions in the kernel driver interface that the kernel exports, and about 700 functions that drivers can implement. And I did about half of these. So I did about 600 wrappers total, and they add up to a decent amount of code. There's also lots of different kinds of objects, and for each object, about 30 kinds of objects, I had to write a recovery procedure to figure out how to release these things back to the kernel. And that, I count that as part of the isolation code. That's sort of part of the object table. The other piece of this code is recovery. This is the shadow driver implementation, and this was about 3,300 lines of code. Now here, this was only for 3 classes of drivers, and there's closer to a dozen or 20 classes of drivers overall. So I'm going to look at how much work is it to implement one of these classes. So I went to my 3 classes, and I counted how much code of this 3,300 lines of code is unique to this class of driver. And it ranges between about 200 lines of code and 700 lines of code. For comparison, I wanted to see how big is a device driver on its own. How does this compare to one single device driver? And so I looked at the device drivers I was testing with, and they were many times larger. So for example, my whole recovery system is about half the size of a sound driver, just as a sense of comparison of complexity. Now, a shadow driver is generic code. Remember, it applies to a whole class of drivers. So I also looked at how big are these classes, and I found there are between 8 and 190 drivers, between 29,000 and 264,000 lines of code. What this means, for example, is that with a network shadow driver that's 200 lines of code, we can recover from the failure of any of 190 different drivers comprising 264,000 lines of code. This sort of demonstrates the tremendous leverage that you get by building fault tolerance into your system this way instead of going and making every one of those 264,500 lines of code perfect. And that's why I think this is a nice approach to improving reliability. So the next question is, well, does it actually work? And again, I'm going to break this down into isolation. Does your system crash? And recovery. Do applications keep working? So ideally, to test the system, what I'd like to do is I'd like to put it on 1,000 machines with 1,000 different devices and run it for like 10 years and see, is this more reliable than a normal system? Unfortunately, as a mere mortal, that was not possible. So the next best thing, which is I took one machine, and I took a virtual machine, and I injected a lot of bugs into a driver. I put in a lot of artificial bugs, and I saw what happened in that case. And the bugs I injected, this was actually a tool that was written at the University of Michigan. The bugs they inject, the tool injects, model realistic, real programming bugs. For example, they'll change the condition of a test statement. They'll leave out a locking statement. It may pass a bad parameter to a procedure or something like that. So what I do is I load the driver into my system. I inject 5 bugs into it, so I get hopefully some failures. And I then test the system with common applications, and I record what happened. A normal system without Nooks, there's 2 things that can happen. Either nothing may happen because the bug wasn't executed, or it executed but had no impact, or the system can fail in some way, for example, crashing, hanging, returning bad data. I then reboot the system, and I do the whole thing all over again. And I did this about 400 times for each device driver. Now with Nooks, there's another thing that can happen, which is that Nooks can detect that a failure occurred and recover automatically. What I hope to see is that many of the failure cases that occur without Nooks turn into recovery cases with Nooks. So let's look at what happened. On this graph, on the x-axis, I'll show you the drivers that I tested. On the y-axis are the number of times the system crashed or hung. In blue is what happened without Nooks, and in red is what happened with Nooks. So here we see with the PCNet 3200 megabit network driver, there were 119 crashes when I injected faults. With Nooks, there was 0. Every one of those 119 crashes was detected and recovered by Nooks. Across the other drivers that I tested, I found that Nooks was able to detect and recover for more than 99% of the failures that occurred without Nooks. In the one case that it did not recover, in this case, the driver went into an infinite loop with interrupts disabled. And so I couldn't actually, Nooks could not regain control of the processor to trigger recovery. And had there been, a box on the side of the machine to do this, I think it would have worked. So this is about isolation. Does the system keep running? It says nothing about what happens to applications. So I did a very similar set of tests, only this time I ran applications that were calling into drivers. And I wanted to see what happens to those applications. So here I have 6 applications on the bottom, 2 for each class of device driver. And again, I ran the driver, I ran the application, injected bugs, and I wanted to see what happens to the application. And basically the way this worked is I sat in front of this, and I did like 2,000 tests, and I measured what does the application do, because it was very difficult to automate this. And I wanted to see, does the application keep working after this happens? So it's sort of a very human-oriented sense of success. In blue here is how many times did the driver fail. And I know this because I can look at either the application stopped working or the system crashed or something like that. And red will be how often did the application fail. And what I found was that in 98% of the case, Nooks was able to recover from the failure and keep applications running when the driver failed. In the cases where it did not recover successfully, there were two things that happened. One, we saw some of those infinite loops that I mentioned before. And the second thing we saw was that sometimes, before we detected an error, the driver would leak corrupt information into the kernel or into the application. So that even after we recovered, the kernel or application still behaved incorrectly. And that's why we didn't get quite as high this time. But overall, we're able to keep applications running 98% of the time. Now, it's important to remember these are synthetic failures. The distribution of faults I injected is uniform across 8 different types of failures. And there's no sense that this is an accurate representation of the distribution of real failures. So you can't say, well, this would necessarily make your system 50 times more reliable or something like this. What you can say is it looks like Mike covered the bases and that it should work pretty well, but we don't know for real. So don't go putting stock into my company yet. So the next question is, of course, what's the cost? What's the performance cost of using this? It's great that it works, but is it feasible to use without really tanking your system performance? So what we wanted to see is sort of for common usage scenarios, what would it look like? Would it work well? Would it be pretty expensive? So I took the same 6 applications, and I measured performance on a system without Nooks and a system with Nooks. And the metric that I use is sort of specialized to this particular application. So for the MP3 player and the audio recorder, these are real-time applications. I can't really measure completion time or something like that. So I measure the CPU load on the system. For the network send and receive, I look at the throughput. And for the compiler and the database, I look at the time to complete a fixed workload. And what we found, again in blue is no Nooks. With Nooks, it's red. What we found was that in the worst case in these tests, Nooks was 3% worse than without Nooks. And on average, it was within about 1%. Meaning you can use Nooks without having a big performance impact on your system. You really can get reliability almost for free. Now, this is only part of the picture of the performance cost. This is sort of the application performance. There's also the question of, what about your capacity? What about your capacity to do other things with your system? So I also measured the CPU utilization. And here we found that there was indeed more of a variation. And basically, it comes down to how often do you call from the driver into the kernel. So for sending data here, this middle bar of network send, the kernel calls in the driver 30,000 times a second to send a packet. On each one of these, we need to do an XPC, which requires changing the page table. On x86, this means flushing the TLB. So we've got an expensive page table change. We've got a lot of TLB misses. We're copying data, so we're blowing out our cache. So that's sort of where the overhead comes from. And I think there's ways to improve this, but at the same time, this isn't that bad. And if you had a multi-core system, you could sort of use different cores on your system to reduce these costs. So the question a lot of people ask is, where do we go from here? Well, one thing that's interesting is, Xen is very popular now as a platform for virtual machines. Could we apply some of this to Xen? And it turns out the shadow driver architecture is very similar to the way that Xen does I/O. They have sort of a stub driver on your guest operating system, and you could, I think, fairly easily incorporate the shadow driver technology there to provide the same transparent recovery stuff into Xen pretty easily. Another thing to look at sort of more broadly is, what do we do about drivers? So drivers have been a problem pretty much since computers were made. And if you look at the history of operating systems research, almost nobody has done anything in it. There's maybe 10 papers over 30 years on device drivers. And the reason is that they're complex, they're ugly. Most research operating systems, people will just borrow existing device drivers, and they sort of leave that section of the paper out. They have one sentence where they say, oh, we borrowed the BSD device drivers, and so we're not going to solve that problem. And so they're really not that great. It's really industry that's been innovating here. And even so, there's a lot of problems. So there's a couple of things I think would be interesting to look at. One is reducing hardware-induced driver failures. There's data from Microsoft where they have the same exact devices, and they have 2 different drivers. One is a normal device driver, and one is what's called a hardened driver that knows that devices can fail and checks to see if the device failed and does some internal recovery. And they found that overall device failures were about 10% of their server failures, but that those machines with the hardened driver failed 70% less often because of device failures than those with normal drivers, indicating there's lots of device failures that drivers could be recovering from that they're not, and we could get even more reliable systems with slightly smarter drivers. Another thing to look at is new driver architectures. Right now, drivers are generally sort of this monolithic piece of code that runs in the kernel, and it's pretty complicated, and I think there's other ways of doing drivers. A comparison here is look at distributed systems. Originally people programmed distributed systems by sending and receiving network packets. And at this point we have RPC, we have broadcast, we have lots of nice technologies for writing distributed systems that make it a lot easier. For drivers, we still have read and write a byte over an I/O channel or something like that. the state of the art is still pretty far behind with drivers, and I think there's new architectures that could make this a lot easier. Some other things that would be helpful to this, the ability to test a driver without a device. Right now, the driver is very intimately tied to the device. And if the device isn't there, you can't run the driver code, which really limits the kinds of testing you can do or the kinds of evaluation you can do. So finding technologies to do this, such as symbolic execution, could be interesting. And then finally, it turns out there's a lot of drivers that are not at all performance critical. For example, there's a Homer Simpson doll that you can plug into Windows that has a kernel mode device driver. This is stupid, right? This Homer Simpson doll is like 1 kilobit per second bandwidth or something like that. It has no performance requirements whatsoever. There's no sense that it's a critical system component that has to be in the kernel, or that it even has to be written in C or C++. And so really, we should be writing device drivers in something like Python instead for devices like this. There's no reason we should sort of force driver writers into this complex world for such simple devices. And so I think looking at other alternatives for writing drivers or simplified frameworks and languages would make this a lot easier. Oh, whoops. So that's about all I have to say about my work. In conclusion, we built Nooks. It's an architecture and a set of components for improving reliability that I think I showed you is pretty effective at preventing crashes. It was compatible with existing code, so there's not a huge cost of adopting it. It had a pretty low performance overhead and had a fairly low implementation cost. That is all. Do you have any questions? Up there. So in Linux, the difficulty in Linux is that the kernel interface has a lot of macros and inline functions, and we needed to change some of those so that you need to at least be able to recompile the code. If you have models such, I think NVIDIA has a model where there's sort of a shim that you recompile for your kernel that has sort of the kernel driver interface in it, but the rest of the driver is just binary code. I think that'll work just fine. It's really the code that has the kernel driver interface has to be recompiled, but that's about it. Other questions? Up there.
We've been working on this for a while. I'm curious about when we might start to see this kind of built into the kernel for some of the more popular systems.
So I have to admit that despite having been a professional software engineer for 8 years before going to grad school, when I wrote this code, my goal really was on getting it out quickly and graduating. And so I did not write what you might call a heavyweight or professional quality, deployment quality implementation. So there are some people around the world who are playing with it, looking at porting it to the 2.6 kernel. The other point is I think this is sort of the first project on driver isolation. And while I think it's the greatest thing since sliced bread, I also know enough to know that the first thing is rarely the best answer. And so I think this idea of isolating drivers should kind of sit and percolate for a couple of years to figure out the right way to do it. So Zen has a model where they move device drivers into a separate protection domain. There's some issues there about what drivers they can run, some performance issues. But that might be a better way to do it. I think the key thing is this notion of getting drivers out of the kernel. And we do see that. Microsoft has something called the user mode driver framework where you can write your USB Homer Simpson doll driver in user mode. So these things are coming along, and not necessarily like this, but this was sort of a genesis of some of these projects. Yes?
So if a driver writer wants to write a new driver, what do we tell them about the shadow driver? Would that be an interface to the OS they now actually conform to, or would it be something that they write themselves?
So if it's a new driver in an existing class, like you're making a new network card, then they don't have to know anything because the shadow driver is based solely on the OS side of things. It doesn't really matter what the driver does. It's really that the driver does what the OS expects it to do, which has to be the case. If you have a whole new class of devices, suppose there were lots of USB Homer Simpson dolls and you wanted to have a shared driver infrastructure, then somebody who has defined this class interface should go and write the shadow driver for it once for all these dolls. If that makes any sense. But so in general, driver writers should not be aware of this. This is really the OS side of the kernel side of things, not the driver side. Yes?
You're talking about recovery. So how do you detect a crash or the hash?
Okay. So to detect a crash, I rely on the processor hardware. So if the driver tries to write to a bad address, something that it's not allowed to write to, or it reads from an invalid address, then the processor raises an exception. The exception handling code will say, oh, look, we're running in a protection domain. Let's call the shadow driver to do something about this instead of either blue screening the system or calling the panic code. So that's one way. The other way is the wrapper code has error checks in it to detect certain bad conditions. It detects when you try to use some piece of memory you already released to the kernel. And there's other bad things you can do. It turns out, and I learned this, that if the network card tells the kernel that your MTU, your packet size is 0, the kernel doesn't really care, but will then sit there and try to send packets 0 bytes at a time. As soon as you send a packet, the whole system freezes up. So I have checks for things, sort of obvious sanity checks on parameters to make sure that the parameters, certain parameters are okay, and that's also another form of error detection.
So you mean you modify all exception handlers?
I modified the exception. In Linux, there's a common body of exception handling code. There's sort of a standard prologue for almost all exception handlers, and I modified that common prologue that says, if I'm in a protection domain, do something else. Because in general, kernel code should not ever generate an exception. There might be interrupts, but there should not be any exceptions. So it was not a huge amount of work there.
My second question is, since you all had some new code with 30,000 lines.
Yeah, right.
So did you evaluate that one in terms of that?
I did not test the reliability of my own code. I know I would find. I know I would find things in there, so it would not have shown me anything new. But it is true. Anytime you add new code to a system, you need to be worried about: are you overall increasing or decreasing the reliability? So my only answer to that is, look, we've got that argument that we have 264,000 lines of driver code, and there's more drivers coming every day, and this whole system is the size of like 2 drivers. So if you're going to add 2 drivers to your system or this, it's not that bad in comparison. Other questions? In the back.
In order to discover some of that tricky kernel behavior, such as the zero packet issue you mentioned, did you simply read the kernel's source, or did you write deliberately badly behaved drivers?
No, I had a lot of bugs in implementation where I was. So there's this issue of you have to copy data from the driver into the kernel, and it turns out that the Linux kernel has these really bizarre ways of doing things. For example, some cases you pass a parameter to the kernel, and then the kernel returns, and then at some future point you fill in certain fields. And there's a promise that's not really enforced that before the kernel uses those fields, you'll have filled them in. And there's no guarantee of this, but if you have a single processor machine and the kernel is non-preemptive, then you're guaranteed that you will run before any other user mode code runs that actually uses this information. And so this was a case where I didn't know that you were allowed to change these things asynchronously with no locking. And so I missed copying this MTU field over. And so I found fairly quickly that my system locked up. So basically the checks I put in were things that I ran into or that were fairly obvious. And to be honest, they had a very little, they found pretty much almost none of the failures that occurred in testing were found by those checks because they were too sophisticated. Any other questions? Here.
I noticed in the slide you had where the increased CPU time with Nooks enabled,
Mm-hmm.
the network driver was the worst. It was frankly double. Can you explain why that was?
Sure. So the network driver, this was a gigabit network card, a very high bandwidth device. It was the highest bandwidth device by a factor of 10 or so. So that was sending packets required sending, sort of calling into the driver 30,000 times a second. And when you send packets in Linux, you don't send 10 packets at a time. You send 1 packet at a time. So every one of those packets incurred this cost of switching the page table and copying things. In the receive case, when you receive packets, modern network cards will basically receive a whole bunch of packets and deliver them to the kernel at once. And so in the receive side, I could receive 10 packets at a time when delivering data. And so the overhead was a lot lower. In the case of the sound card, the sound is, this is 128 megabit per second, 108 kilobit per second MP3. It's just low bandwidth. So there's not a lot going on. In the case of the disk driver, there was more. It's a pretty infrequently called thing, about 60 to 100 times a second. But there's a lot of code that runs there. And because we flushed the TLB and we had to do data copying, there's a lot of sort of microarchitectural cost of refilling the TLB and refilling the cache and things like that that account for the increased CPU. Anything else? Yes?
So how long did, for example, network drivers take to reload?
So it depended on the card. The best case was the PCNet 32 driver, which took about 1/10 of a second. The worst case was the Intel E1000 driver that took 5 seconds. And basically, part of this, it really has to do with how long does the driver take to initialize. So when you boot your system, initializing the E1000 driver takes 5 seconds. So like Microsoft has a goal, either for XP or Vista, of booting your system in 13 seconds. And that means that you could not use this E1000 driver in that environment. And basically, the E1000 card is going out and probing your network and sending packets and seeing what's out there and sort of doing all this really heavyweight stuff. And it would be great, if you were willing to modify drivers, you could sort of have the driver say, here's the state that I need. And then when you reinitialize it, you could say, well, here's the state you already discovered. I promise you the hardware hasn't changed. Just use it and don't do the probing. But I didn't really want to change drivers that way.
So, but wouldn't that make your shadow driver dependent on what it was trying to shadow? Because, for example, if it's going to come up in a 10th second, then if you waited 5 seconds, then there's obviously something broken.
Mm-hmm.
But if it's going to come up in 5 seconds, and the next attempt is 5.1 seconds, then you
So
want to do that.
So the question is, does the shadow driver sort of depend on how long it can take things to recover? So in a distributed system, when you look at automatic recovery, there's this question of you don't know if something else failed because it's on the other side of a network, and you can't distinguish sort of delay from things not working at all. Here, because we're in a single kernel and shared memory in one place, we can actually know that recovery is proceeding. So we're not worried that recovery is taking too long because we know it's taking place. And so if, for example, during the startup process, we call into a driver and it never comes back, then we have a watchdog timer that goes off in like 30 seconds. So if you have something truly exceptional that can take 30 seconds, we'll detect it. But for shorter things, we don't really worry about that because the kernel is in control at all times. Any other questions? Yes?
What about tuning in terms of automatically loading, using Nooks for certain drivers and not others, depending on the number of problems you've had?
Mm-hmm. Yeah, we certainly thought about that. The question was, what about tuning? If there's a performance cost, you might not want to use it all the time. And I only showed you, to be honest, running Nooks with one driver at a time isolated. And so running more than one, you could have, you might get more than double the cost or something. So you might want to figure this out automatically. And I think that certainly would be possible. To do that, though, you really need to have, it's harder to do that synthetically because you really want to have a more realistic bug workload to work from. Synthetically, since we control when the failures happen, it's trivial to adapt to your own synthetic workload. Yes? Yes. I did. There was a network card from SMC or something like that you could just not soft restart. You couldn't, on normal Linux, you couldn't unload the driver and reload the driver. And it turns out that one of the most common Linux devices, the 3COM3C59X driver, which used to ship with all Dell machines, had a bug where if you unloaded it and reloaded it, it would drop 1 out of about 20 packets. And so your bandwidth would just go in the tank because you'd get all these TCP level retries. And that was fixed at some point. It was a problem that I detected because I was doing all this recovery. I also saw another driver from 3Com itself where if you failed during initialization, it would double free a kernel buffer, causing problems. Now, it turns out normally you never fail during initialization, so nobody else besides me saw this, but it was a great success, I thought, that Nooks could detect a failure, real bugs in drivers this way. And then the other thing I saw was, shadow drivers have this model of how initialization works. And it turns out that some drivers don't actually follow the rules. So Intel, again, the E100 network driver, you call it, you say, open, initialize, start yourself. And the network driver says, well, I will in the future, and it registers a timer. And then only when that timer comes back does it actually finish initialization. So this is fine normally, because normally in Linux, when you load a network driver, there's a user mode piece that goes and resets your network parameters that takes half a second or something, and the timer is only about 100 milliseconds. When you're in the kernel and you're just calling everything sequentially right in a row, we turn around and call back to start sending packets before the timer had gone off and it was not initialized yet and everything broke. So we had to sort of finesse things a little bit and put in some artificial timing to make that work out correctly. Other questions? Okay. Well, thank you all for having me. It was great to present here. And if you have any questions, feel free to contact me at swift@cs.wis.edu. Do you have a question? No? Okay. You're just getting ready to clap. Okay. Well, thanks.